So let's talk about some very basic concept in quantum mechanics, or at least in our picture, right? We always talk about this two-level system. And then some of you might wonder what this looks like. And then we always talk about you can decompose or you can express your wave function as the eigenstate like this. Okay. So what does this mean? And is there anything we can do to at least visualize all this process? And the first example I want to show you is harmonic oscillator. So in a classical picture, harmonic oscillator it's kind of moving around. It's certainly a position, and the speed, the momentum. But in quantum mechanics, we kind of say that you have an eigenstate, and then for each mechanical oscillator, its eigenenergy is its frequency, h bar, and then times the integer number. And fortunately, these days with YouTube and Wikipedia, some people have made this very nice cartoon here. And then this is a classical picture. What happened to a mechanical oscillator? It's kind of doing this oscillation, right, left and right. And this is actually the ground state of your harmonic oscillator. And one color is, well, this one has both real part and imaginary part. Okay. So what happened is they're doing this oscillation, okay, and then the wave is centered here. So it's very different of picturing a classical oscillator and a quantum oscillator, although they are both something attached to a spring. And this is a ground state. This is the first level excited state. You can see that there's two knobs here, okay. And then going on 3, 4, and actually these two are irrelevant. I think they're superposition state. Okay. So this is kind of how the wave function looks like, okay, when you plot it in this way. And then, so when we say you write down an equation like this, the wave function really look like this one. Okay. I think this one they take both the imaginary part and the real part. They just calculate they probably only show one, like imaginary or real part or imaginary part. So here I think we can see something is like their behavior is really like wave. It's not like mechanical oscillator, they're moving around. It's really like you have a string, and then it's attached to a wall, like on these two ends. It's like your violin or your piano. And then this is the wave, right? You have on these two ends, you have 0. On the center, you have maximum. And this one is the first excited state that you have a knob in the middle, like 2 wave. So if this is cosine omega t, this is cosine 2 omega t, and this is cosine 3 omega t. Okay. And this simply shows you that when we talk about state 1 and state 2, we can always calculate it. There's a function you can reference to. Okay. And so this is the This is the harmonic oscillator. Then what about the hydrogen atom? So for the hydrogen atom, it's somewhat similar, but you can also plot the wave function out. But the hydrogen atom, if you think about it, it's a three-dimensional thing. Okay. What we do here is we're probably looking at it from the top and see the projection. Okay. And for absolute ground state, it's something look like a sphere. So it's totally symmetric. When you look at more excited state, then you start to see like this. It has ring structures. What it means is that the higher color, well, the brighter the color, it means the more probability you can find the electron there. Okay. So it's so it's different from our original view, like saying an electron is orbiting around the core, the nuclear. It's not always like that now. It has a distribution. And I think what's more even interesting is these are quantum numbers. When you go to other state, there's some other state look like this. It's kind of not really symmetric. Well, it's symmetric, but in a different way. Okay. And so the electron can actually, what they can do is that when they jump from the ground state to the excited state, let's say jump from here to here, the electron distribution changed from this one to this one. Okay. Previously, in the classical picture, we think it's the electron doing circular orbit, and then when it jumps to a higher energy state, the orbit becomes a little larger. Now it's you actually have to change the distribution of the electron density, and because of this, they look different. So when you do calculate like mu12, right? The mu12 is, by our definition, mu12 is 1 qx2. Right, 1 and 2 x. So the left-hand side, you take one state. Right-hand side, you take another state. And then you multiply x, and you do the inner product, the integral. So if you kind of really do this calculation, you will see if you take this is ground state, this is excited state, the number is 0. Okay. But if you take this, the number is not 0. And well, you can easily do it in mathematics. You can look up the equations for this. But what it really means is that people later figure out is that the photon has angular momentum. And this L are also angular momentum number. So when you emit a photon, you need to conserve angular momentum. So that's why you have to jump 1. Okay? You can jump from here to here and here to here, as long as the difference is 1. Okay? It can be 1 and minus 1. This is kind of, I think some of you might have learned it in chemistry. This is selection rule. And quantum mechanics really can help you to understand that. Okay. So this is ground state. Ground state is just a solution to Schrodinger equation, and then it can look like this. And the next thing is this one, the superposition. We say that a state can be in a linear combination of ground state and excited state. And you have some probability in 1 and some probability in 2. And this can be a little bit confusing. Okay? And that's perfectly fine, because there's a huge argument when quantum mechanics was first established what this really means. And the sharp debate is actually proposed by Schrodinger himself. This is the original of Schrodinger's cat. Okay. So what Schrodinger proposed is that, well, let's write down a state. One state is nothing happened. The atom keep in ground state. It's doing nothing. Excited state is that it emit a radiation. Let's say emit a gamma ray or emit a photon. And then what he say is that, well, this is your atom. Okay, you can emit something, and then here you have a detector. Okay. When it receives a photon, what it does is that it triggers a signal to release some poison, to poison the cat. I don't know why Schrödinger chose a cat, but probably he had a dog, so he chose a cat. So then what he argued is that we say there's a probability of A and B, and then when we do the measurement, it collapses into either ground state or upper level state. You can never see an atom like in when you observe it, it has to be one of them. And you have the probability of A squared to see in ground state and the probability of B in upper state. Okay. And at that time, I think it's still right now, the argument is that before you make the observation, it's in a superposition state. But when you make the observation, it collapses into 1 or collapses into 2. So Schrödinger thinks this is kind of a ridiculous situation, because if you don't look at let's say here's a cat, and they're all in a black box. Okay. If you don't look at it, it's in a superposition state. Your cat can be both alive and dead. If you look at it, it can be dead. And that's something, if you think about it, how can the life of a cat depends on whether you look at it or not? It should be whether the cat look at it or not, right? It's like think about it. We live on Earth, and then quantum mechanics says that there could be a state, if an alien look at us, we all die. Okay, it's kind of ridiculous. But this is what quantum mechanics suggests. And this is a paradox, and Schrödinger himself proposed. And unfortunately, I think in 2000, a group, I think in Europe, kind of actually, they're able to manufacture this Schrödinger cat state. But it's not really a cat. It's I think it's a crystal. Like the crystal, a lot of atom can be either one in excited state or in ground state. So there are many interpretations on this. One often is becoming more and more popular, especially in movies, is multi-universe explanation. And it might sound ridiculous, but a cat both alive and dead and can be determined by you is also ridiculous. So they're equally ridiculous, and they're equally good enough to explain the experiment. So you cannot say one is correct or one is wrong, okay, unless the experiment tell you that. So what the multi-universe explain is that, okay, when you look at it, you enter the universe where the cat is alive, and the cat entered the universe. So you create two universes. In one universe, the cat is alive. In one universe, the cat is dead. And when you look at it, while you found the cat is alive, you enter that universe. That's it. The cat itself can enter a different universe. Okay? And these two universes cannot communicate with each other. That's the point. You cannot communicate with each other. And I think many people are working on this. And but their direction, of course, is to make communication between two universes. Otherwise, you really can't tell, right? We are living in one universe, and they say you have many universes, but then you can't contact them, you can't measure them. Then you're creating a situation where you cannot prove yourself, and other people cannot disprove you. And that's not really science. That's it's on camera, so I wouldn't say it. Okay, it's other things people have created thousands of years to explain the nature. Okay. And you can't disprove them or prove them. So I think here is a micro change. Let's see. And there's very nice movies about superposition state, and somehow they also use the knowledge of what we've learned, like light inject into an atom and then have the oscillation, Rabi oscillation. Let's see if it played out. No sound? No. That's the disturbance. So this part mainly says that your atom can be in superposition state. It can be this state, it can be that state. It can be in both of these states together. And then it goes to the two-level system. Okay, this is ground state, and then excited state. And you can be in a superposition of both of them. Okay. And then if you look at it, only one can be seen. Okay. If you close your eye, it becomes back to the superposition state. And of course, people we can't really see atoms, so you send out light to probe the atom. And then here is what our knowledge, come into play. We can see the Rabi oscillation we all saw a few classes ago. So the A and B start to flip from 0 to 1 and 1 back to 0. And this part, it kind of drew one scenario of the coherence. Is that if you're in a thermal position, then you can collide with other atoms. And this would decoherence of your state. And then what will happen is that it slowly go into, instead of oscillation, it go into a steady state. And the steady state is something we want to solve in this class. And you might wonder how all this is related to you. The superposition state is actually one of the core concepts in quantum computing and quantum information. So if you look at this, they too, there's a plus sign here. They too don't have. Let's do it this way, okay? If you operate something, right? If you have information, let's say ground state means 0, upper state means 1 in information, right? 0 and 1 is the information. And when you do operation of A, on this state, then what it would do is it would do operation on one state and operation again on the excited state. So it's doing calculation of both 0 and 1 at the same time, right? In classical computer, if you try to calculate, the input is 0, you calculate 0 first. And if you want to know the answer of 1, you have to wait for this calculation to finish, and then input 1 and calculate again. Okay? So it's you have to wait. Here, you don't have to wait. They are calculated at the same time. Okay? And this becomes very advantageous when you have a lot of them. Okay, so this is one of the key concepts in quantum computing. And all of you guys might have a career of 30 years ahead of you. And then this is an argument I want to make is that there's a slight chance that you guys will be work with something related to quantum computing. Okay, it might not be asked you to build a quantum computer, but your boss, or if you're working in a research position, like in a company, some people may ask you, say, oh, this company offers quantum computing service. can you optimize our product using it, like an algorithm, like a service? Can you do that? Now think about the math here. If you look online, there's only one quantum. Well, chemistry probably have quantum, but chemistry won't work in the same position as you guys. So in physics department and engineering department, there's only one quantum mechanics class that's offered by physics department. If you check the enrollment number, only 40 enroll per year. And then we have 700 undergrad at least in EC engineering. So if you know quantum mechanics, and then somehow in the future you work with something related to this, you're automatically the top 10%. You don't even have to fight, right? You don't have to fight. That's the argument. Spend some time on quantum mechanics to guarantee you a spot in the future. It's that simple. Okay? If you don't use it, that's fine. You can build yourself a live and dead cat and have your dog fight with it. So you can enjoy your life. It doesn't matter, right? So when you make some career choice, always gather some information and do some analysis on it. And you can see, well, at least it gives you some motivation, okay, on these things. And by the way, one area that is happening right now, unless you guys didn't know, of course there's AI, right? Artificial intelligence. But there's actually quantum AI. Why quantum AI? Because if you think about of our neural system, that's how we think. Neural system doesn't work like a computer. It can actually work parallel. That's exactly what quantum computer can do. Okay, so quantum AI is one direction. And then we actually have a group of our undergrad classmates. Some of them are trying to, they're trying to switch career and then go into AI. And then a few of us talk him out of that and say, well, you have physics education for 4 years. You should just jump into quantum AI and then be a few years ahead of other people. And then instead of doing AI, okay. So that's enough about the. That's enough about the quantum mechanics. Let's keep on. And we're almost finished with our quantum-related stuff. Okay, if you feel like you can't handle it anymore, that's fine. It's over. And because next week is exam week, so the content for next week will not appear in your final exam. Okay, so even you don't understand it, that's fine. So this week we're going to finish the two-level system, and then we are going to associate it with laser. How you build laser. And then next week this is something I think it's a bonus because some of you actually are very familiar with quantum mechanics. I know that. So next week we're going to talk about the full quantum picture of, why I erase it? Okay, of the two-level system. Okay, you quantize your EM field, and that's actually very useful. Could be very useful because the best way to communicate to send out quantum information is just like send out classical information is to use light. We travel at the speed of light. So learn how to do that, or at least see it can be done, can be helpful. Okay. So let's return to this. E cosine omega t, and then you have okay. Last time we say that we want to calculate when you have this atom, we want to know the refraction index. Like if you have your glass, you want to know the refraction index of your glass. So to do that, we already say we need to calculate the polarization, right? The polarization is density of the atom, and then dipole of the atom, and then do this average. So this is on average what you will see of the polarization. And we define the dipole of ground state to excited state with this, and then right, and then we say, well, this is a complex conjugate of this part, so if you can solve this, you get your polarization and also you get your refractive index. And what is P12? Kind of say it's this one. If you go through the math, okay. And then later we construct this equation for P12. This is the content of last class. Is the minus okay. And then also we use previously from our two-level system, we kind of know what will happen if you have electrical field on an atom. Then you create a coupling between ground state and excited state, and the coupling look like this. And then BT. No. Okay. And you plug this in, and we can arrive at an equation of P12, right? And I kind of show you how to solve this differential equation where P2, P1 are the probability of in state 2 or state 1. Okay. And I think we show you how to do the math. And then I think we stopped here last time. Okay, this is where we stopped last time. And this is unfortunately very long, this integral. But we kind of have our best friend approximation here. So in the approximation, we assume T2 is very small. I think the camera is about to shut down. one thing kind of ridiculous is that, do you guys know why the camera have 30 minutes limit on video recording? I think even everyone's iPhone has that. It's about a tariff posed by Europe. Okay, Europe tried to protect their video camera industry, and then they have to define what's a video camera, right? Nowadays, all the camera can take video. So I think one senator just say, oh, 30 minutes, and here you go, 30 minutes. And then if I want to purchase a camera that can record more than 30 minutes, I think nowadays the price is about $1,500. Okay, $1,500. And this camera is actually a weather-sealed camera, waterproof camera is only $800. So kind of ridiculous. Okay, so so T2 is very small. We return here. T2 is very small, and then what we can see is this term here. Okay, there's a minus sign. So what it means is that this term can be very large. Like, let's write it down: E T2 T minus T. Okay. This term can be very large. Sorry, this term is actually approaching 0 unless right. For any other numbers, because this is small, this term explodes and this entire thing goes to 0, unless you have t minus t prime approximate to on the level of t2. So what this tells us is that if we assume t is much larger than t2, we can always do this because we choose a frame, right? We choose a starting point of our t. If we can do this, then this one goes to minus infinity, because at time 0, you plug t in, and then this thing explodes. Okay, this thing converges to 0. So you can do this. And then the next thing we want to do is to think about all the other time-related terms here. So what's the rate of P2 and P1 change? Okay. We know that you have oscillation, right? You can input your light, and then to move atom from lower state to higher state. And that time scale, or that oscillation, Rabi oscillation, is defined by omega r, right? Rabi frequency. So the time to move an atom from 1 to 2 is the inverse of your frequency, right? The inverse of a frequency is a time. So now we can make another approximation, T2 much, much smaller than, okay? So decay is much faster than your Rabi oscillation. Before you finish one oscillation, you already decay. What it means in this integral is that our integral only happens around T2 time. Okay? And within this T2 time, you haven't finished one Rabi oscillation, or you barely move, actually. So in the integral, let's see, Pj equals 1 to T prime T. Okay. Only when T prime is close to T, this one doesn't go to 0. And because the change is very slow here, so you can approximate yourself to T. And the same thing happened to the electrical field. right? Because if your Rabi frequency, you haven't moved your atom from lower state to upper state, then this one doesn't change as well, right? So okay. And with this two approximation, then it's kind of nice now. By the way, this approximation is true for most classical objects, like all the materials. I shouldn't say all. Most of the material. Well, let's see. Most of the materials in room temperature satisfy this condition. I'm not so sure about like graphene or kind of things that, what they do, but for most materials, this condition is okay. So we can take this because it's now not t prime, it's t, and the integral is about t prime. So you can move this out of the integral. So P12 t equals minus I U12 e t, okay, and then P2 t minus P1 t, and then you have the integral C2H bar. You have the integral of minus infinity to t dt, okay, e minus I omega. Oh, this one is t. This one also can go in the front. Okay. E minus I omega plus T2 t. Okay. Minus infinity to t. Here's the minus sign, they cancel each other. I omega plus T2, okay, t, and then t prime. Okay. Here is another one with t prime minus I omega t prime, dt prime. Okay. Yes, I think it's accurate. So this integral, I believe most of you can solve it, right? It's just like this. Okay. You have exponential term, and then what this equals to alpha e alpha x, say a and b, right? Just regular integral. So P12 equals all these things in the front, and then I omega minus omega plus T2. Okay, this is your alpha. And then you have E I omega plus T2 t minus I omega t, okay, minus right, you have this one you plug in, t goes to minus infinity, and then when t goes to minus infinity, this term goes to 0, right? So you can cross away this term. So I think we can write it down. Let's see, somewhere here. Okay. So P12 You plug it in, you see these two? Okay, this one and this one, they two cancel each other. Okay. And the only thing left is this one, minus I omega t. So what will happen is that you get minus I mu 1, 2, okay, and then P2, P1, 2H, and you see this. Right, this is our E field. This one, plug it back, is a polarization. So the thing in the middle gives you the refraction index, gives you the chi. Okay. So let's. I think we can erase all this. So let's write down P12. By the way, there's a simpler method. We can actually solve this. But it's very easy to make mistakes, so I include it in the class notes. But it's not totally necessary whether we should, discuss it or not. So P12 T equals okay, and then the real P equals N mu 12 P12 T time plus its complex conjugate. Right? And from now on, we only focus on this minus omega, this frequency part. Okay, there are, you can change. Well, you can switch between cosine omega t and this, regularly. It doesn't matter which one you choose. So we can get pt, okay, n times p2. P2 is probability in excited states. N is the number of atoms per unit volume. So when these two times together, it gives you the number of atom in excited state per unit volume. Okay. So let's do this one. Minus I 2H bar. You have N2. The number of atom in excited state minus N1. Okay. Number of atom in ground state. Okay, like this. And then following, we have mu12. And this is something kind of, we kind of didn't derive this in the class, but later you can check out the textbook if you would like to. But actually, the correct form is not mu12 square. It's mu21, and then you do this convert. So the reason is, well, the reason we get mu12 square, this mu12 times this mu12, is because we assume mu12 equals mu21. So that's just a natural result we get. If you don't make that assumption, people can show that this is the result, and this is not time. Okay, this one right together with this one, this is a tensor. We explained before, right? The polarization. This is a rank 2 tensor. When it times with the field, it reduces one rank and become rank 1, and rank 1 is a vector. So this is actually the correct form to write it. So even if you plug this to here, the way to write it is mu12, mu12, okay, instead of times. Okay. But like for most material we work with, I think a lot of them, well, you care, but like in this class, we don't care. Okay. And then you have E, right? Yes.
This T means tensor or
it's transpose. Yeah, so usually you write it down as, let's say, 1, 1, 1. And then the transpose is, I'm not sure if this is complex. Yeah, probably this way. Yeah, so when you times them together, it gets you a matrix. Transpose, yes. And then because of we know P is defined as epsilon chi right, we all know this from classical EM field. Then we get chi. Okay, finally we get chi. I'm not going to repeat it here. Okay? Kind of waste of our time. And then the next thing from chi is still not straightforward enough for us to use. We know n squared equals chi, right? Or we can write it down as, no, n squared is not chi. Yes, sorry. So let's write it down. xd equals epsilon r e equals epsilon e. Right? This is how we write it. And then you get epsilon 1 plus chi e. So we have our relative permittivity equals 1 plus chi. Okay. And then when we solve Maxwell equation for propagation of light, we kind of know chi, we know this, right? The refraction index square equals the relative permittivity. And this gives us what we want, n equals, and chi is, this stuff, a huge stuff, okay. So at this point, we have to kind of focus ourselves on what's interesting and what's not interesting, okay. The interesting part, well, the refraction index, because this is a complex number, right? You see here, this is a complex number. So your chi is also a complex number, and so is your refraction index. The real part of the reflected index, it's important, but kind of you can measure it directly, right? You don't have to go through all this trouble to solve this. You have to know there's a reflective index. It reduces the speed of light and it gives you, refraction. Okay. So what we care about is the imaginary part, because the imaginary part gives you gain and loss. And gain and loss is kind of universal, right, for all the material. And gain is the thing you need to make a laser. So let's write down how we can do this. So for propagation wave, minus I omega t ikz, right? This is a propagation wave. C now. And k is 2 pi n lambda, right? So your E equals to E now. And here you have your real part, I 2 pi n real lambda z times the imaginary part. Imaginary part times with the I is minus, right? Imaginary of the n real plus I in imaginary. I times this I give you a minus. So your 2 pi in imaginary, okay, lambda z. So if n imaginary is smaller than 0, then you have gain. This one grows exponentially. Okay. And if you have imaginary larger than 0, then you have loss. Okay. And when you, well, I don't know if any of you do plasmonic or you know plasmonic. So plasmonic is you use metal to do photonics, okay, to do optics. And in plasmonic, you have to keep the imaginary part all the way, always, because the imaginary part sometimes can be larger than the real part. To think about it, there are two ways to think about it. One is all the metal are not transparent. They absorb a lot of light. So they must have a very large imaginary part to absorb the light. The second one is in the metal, there's a lot of free electron, right? This free electron can interact with your light. And that's why the light can be absorbed very efficiently. Okay. So here, so we want to solve an imaginary. Okay. And again, we want our life a little bit better. We don't want to work with it's actually not, we don't want to work with materials with large imaginary part. It's just most of the material we're interested about has very small imaginary part. And also we can set this to 1, because it doesn't matter. Real part, we don't care about it. So what you will see is chi. Assume chi is much, much smaller than 1. This is not necessary. If you think it has a large real part, it's fine. You just split the real part and imaginary part and just assume the imaginary part to be very small. You can arrive at the same answer. It doesn't matter. What this can help us is when you write down n 1 chi, this will approximate to 1 plus 2 chi, right? If it's very small, we have this approximation. And now we can use the chi to get the refraction index. Let's write it down first. One plus, okay, this part, and divided by epsilon, okay. and there's a 2 here. So 4 epsilon h bar is here. Mu 1, 2, mu 2, 1 transpose. And then n2 minus n1. Okay. And this I is disturbing, right? So we multiply I both here and here, right? I times I minus 1, this one cancel out. And this one times I gives you a minus sign here. So you have omega, okay. Let's just double check. Okay. So the imaginary part, we now just calculate this one. Okay. So what we can do is very simple mathematics. You times this one minus IT plus, both up and down, and then you get n equals 1 plus mu 1, 2, mu 2, 1, and 2, and 1, omega plus, sorry, this is minus I T2 So you see that, let's restart this. So you see that the sign of the imaginary part completely determined by your n2 and n1. It's a population inversion, okay? And let's write it down even better, right? And imaginary equals to minus sign coming out, minus mu 1, 2, mu 2, 1, n 2, n 1. Okay, you see if n2 larger than n1 means there's more atom in upper state than lower state, then this is a negative number. And what negative number mean? You have gain. And have loss. Okay. So this is why when you build a laser, you need population inversion. Okay. When n2 is larger than n1, it's called population inversion. And I think last time, probably 2 or 3 classes ago, we mentioned that in this 2-level system, 1 and 2, if you don't have anything, you just let it sit there and let it be thermal equilibrium. We kind of show that like 99.99% of the atom will be in ground state. So what it means is that for most material, if you don't pump it or you don't do anything about it, you will have n2 minus n1 This is most dielectric material when you don't pump it, when you don't do anything about it. And what this gives us? This is plus sign. This is minus, plus sign. So for every material, it's actually absorbing light. That makes sense, right? It can't give you light, otherwise it's back to the joke. You won 2 Nobel Prize, one in physics, one in Nobel Peace Prize. Okay, nobody fight for oil anymore. And so now let's talk about how actually you can inverse this population, right? Let's give a very simple example. Okay. This is semiconductor, okay? Lower band, higher band. And then what you can do is you can add a bias. I think people usually either call it voltage or current. Okay, add a bias, voltage, or current that can move electron from lower band to higher band. Okay. So this is one way to do it, and also this is how most lasers are made these days. Okay, people no longer use this the energy level in your atom. That's because you can't tune those wavelengths. Here you can easily engineer your band gap by doping or by changing the materials in your semiconductor. So this is one way to achieve pumping. Okay, and another way to achieve population inversion is we call it optical pumping. So this is your ground state. This is your excited state 3. This is the state you want to make laser 2. Okay, you want 1 and 2 to create laser. So what you can do is you can have a lamp. Okay, you can shine light at this frequency. It doesn't have to be a laser. And some of the atom will absorb light to here. And then quickly, this has to be done internally. Like some atom can do it, some atom cannot. Okay, this 3 state will quickly move the atom to 2 states. Okay, by dissipation. This is matter stable state. This is stable state. So this is actually how the first laser was made, using this optical pumping. And optical pumping is still widely used today to create lasers at 1 micron wavelength. Okay. And also all the green laser pointer has optical pumping inside. Okay.
Before you erase,
yeah.
I think the imaginary part needs a 1/T2 factor.
Oh yeah, you're right. Thank you.
No, I mean going from that line you just wrote on down below, right? Because the imaginary part has a 1/T2.
See, you.
Over there, yeah.
Yep, right.
And from your notes, you have.
I think I missed a factor of 2, right?
Yeah. So in your definition of the polarization,
I think there's a 2 here, or.
Yeah, and you're adding the complex conjugate.
Yep.
For your definition.
Yeah. Okay. Yeah.
Over there.
Yeah. So this could be 2, depending on the definition of P. Yeah. Thank you. Very good. Let's see if we should stop here or. Yeah, actually we should stop here, but just to start a little bit, for next class, we want to go through lasers, how to make lasers. So today, after finishing this content, you already understand what is an optical amplifier, right? You inverse the population, you shine the light, and then you amplify your light. And nowadays, you can actually buy a very powerful amplifier with a reasonable amount of money. For example, with about 10K, you can buy research level 10 watt laser amplifier. Okay, you can input 1 milliwatt and amplify to 10 watt.